Today we're going to do an activity, the purpose of which is to verify the law of conservation of momentum. We're going to take two dynamics carts, we're going to send one toward the other one, they're going to collide, and then they're going to head off as one object afterwards. We know that the law of conservation of momentum should apply there, it should hold there. Today we're going to see if in fact it does. Last couple weeks, we've been saying that the law of conservation of momentum holds. We've been doing lots of problems assuming that it holds. Today we're going to make sure that in fact it does hold. There are three variables. There's the manipulated variable, there's only one of those. There's the responding variable, there's only one of those. And then there's the control variables, there's a bunch of those. The control variables, of course, are those variables that stay the same. I'm not going to tell you what the variables are in this experiment. I will describe the experiment for you in just a moment here, but you're going to have to determine what the variables are yourself. Now, I will give you a hint. Your hint is to look at the graph that I've told you to plot in the analysis. You know that every time you plot a graph, the manipulated variable goes on one axis, and the responding variable goes on the other axis. So if you look at the x-axis and you look at the y-axis of the graph that you have to plot, that should tell you what the manipulated variable and the responding variable is. The control variables, again, everything else that's kept the same. All right? How are we going to do this? Well, the basic experimental setup is the diagram that you see on the left-hand side here. You can see that we have a triple beam balance scale right here. Okay, that's going to be used to find the mass of two different dynamics carts. Dynamics cart number 1 and dynamics cart number 2. Notice that they look a little bit different. So when you go to perform this experiment and take your materials for the experiment, make sure you take cart number 1, the silver one, cart number 2, the black one. On the end of each of those dynamics carts, there's going to be a little piece of sticky tack that you're going to put on. The purpose of that sticky tack is that when you roll cart number 1 towards cart number 2, it's going to stick to it, and then they're going to remain as one object after the collision. This thing that you see right here is a motion sensor. It's plugged in to this thing right here that we call an Explorer data logger. The motion sensor will determine several times per second exactly where the moving cart is, and then it will translate that ultimately into a graph once we plug this Explorer into a computer. So this is going to actually collect data. It's going to feed it to the Explorer. We're going to plug the Explorer into a computer, and then we're going to get position time data for the motion of these carts. Does that make sense? Here's essentially how it's going to work. You're going to send cart number 1, you're going to start cart number 1 maybe 10 centimeters away from the motion sensor. You're going to use your finger, you're going to push it. Just before you push that, you're going to start the data logger. And the instructions for using the data logger are on an instruction sheet that's at the back of the room right now. So you don't have those in front of you right now, but you will have them in front of you when you go to actually perform the activity. You're going to start the data logger, you're going to give cart number 1 a little bit of a push. It's going to collide with cart number 2 maybe a second later, or maybe a fraction of a second later. You're going to stop the data logger collecting data after they've had a chance to move a little bit. We're going to get, ultimately, a velocity of this cart before it collides, and then we're going to get a velocity for the two carts combined after they collide. In other words, a VI and a VF. Does that make sense? It's not that difficult. In fact, it's so easy that I'm going to have you repeat that 7 more times. You're going to repeat it 7 more times with different initial velocities. So you're going to send it down with an initial velocity, cart number 1. In the first trial, you're going to record your data, and then you're going to do another trial with cart number 1 moving at a different velocity. How do you control what velocity it's at? Push it differently. Push it harder. Push it lighter. What is the exact velocity? How do you know you have a completely different velocity than you had in the first trial? Well, you don't. If we do enough trials and we end up having a couple of them that are pretty close to being the same, it's not a big deal. In the end, you've done 7 trials. Surely you're going to have at least 5 or 6 of them that are different velocities. Does that make sense? This little thing over here, just an aside, this is the top of the motion sensor. this thing right here. There's going to be two settings on the top of the motion sensor. There's a setting for measuring the motion of something that's far away, like a person walking away, and there's a setting for something that's close by, like a dynamics cart that's nearby. You want the little switch to be over here by the dynamics cart. So if it's not there right now, make sure you put it there. Does that make sense? After we've collected our data, we're going to plug it into a computer. We're going to plug the data logger into a computer. There will be a couple things that pop up. Basically, when things pop up, click No, especially this one. Your data logger is going to want to update some firmware. We have 8 data loggers, 4 of which people have attempted to update the firmware, 4 of which no longer work. Those are the ones where people have tried to update the firmware. Click No. If you click Yes, we will need to spend another $270 on a new one. So if you click Yes, we will have to get a new one. It's as simple as that. So click No. If in doubt on anything, click No. After that screen, you're going to see your graphs come up. Now, I only have a couple of graphs come up because I only did 2 trials as I was trying to show you what to do. You're going to have 8 or 9 or however many trials you end up doing, different sets of data. It's going to look something like this. Now, this is pretty good data, but we don't want to view them all on the same graph. We want to view them on separate graphs. So what you're going to do to view them on separate graphs, first of all, you're going to actually click on this little button up here. This is going to allow us to remove the lines. We don't want the points connected. We want to draw lines of best fit. So we want to drop those connected lines. Click on this little button. Again, the instructions for this are on the sheet at the back of the room as well. Click on this little button. Then it's going to give you an option to connect lines. That box will be checked. You want to uncheck that box so that the dots are no longer connected. Does that make sense? Then you're going to click on this. It's going to give you an option to view all of your different trials or to view no data. You want to click on View No Data. Then you're going to get a blank piece of graph paper. Then you're going to click on your first trial. So you're going to click on trial number 1. That's going to give you a graph that looks something like this. One graph without dots connected. Tell me what this part of the graph, please, represents. What's going on right there? That's before I pushed it. Everything was at rest. Now we've got something going on right here. It's moving, okay, position versus time. It's moving. It appears to be at a constant velocity. But then something else is happening right here. It's moving again, but it's moving at a different constant velocity. What's happened right here? The collision. So it's moving at a certain speed, cart number 1, then they collide, and then cart number 1 and 2 combined move off with a lower velocity. Why do they move off with a lower velocity? They have the same momentum, but more mass. Same momentum, more mass, it's going to be a lower velocity. You're going to get 8 or 9 different graphs that look like this. In the end, you're going to save each of these graphs, and you're going to email them to you and everybody in your group. So everybody needs a copy of each of these 8 or 9 graphs, depending upon how many trials you have. With each of these graphs, you're going to have to find the initial and the final velocity. How are you going to find the initial velocity and the final velocity? Draw a line of best fit. Get the slope. That's the initial velocity. Draw a line of best fit. Get the slope. That's the final velocity. Once you've done that with 7 or 8 or 9 or however many trials you have, you're going to record your data on the table that looks like this. That's on the handout that I already gave to you. 7 or 8 different initial velocities of cart 1, 7 or 8 different final velocities of both carts combined. Of course, you need the mass of both carts as well. Once you have that data table filled in, you're going to plot your own graph. Now, this is kind of the hint that I alluded to earlier on. The graph that you plot in your analysis is going to be final velocity as a function of initial velocity. When you plot that graph, it should be a straight line. If it is, I want you to draw a line of best fit. Then I want you to do something that you've never done before with a graph. You're going to determine what the slope means. Some of you are thinking right now, hey, I've determined what the slope means for some graphs before. Physics 20, we learned that a position time graph, the slope represented velocity. In a velocity time graph, the slope represented acceleration. We've done that before. The only reason you know that the slope represents velocity or acceleration in Physics 20 is because your teacher told you. You didn't figure out what the slope represents. Your teacher told you what the slope represents. Now we're going to learn to figure out what the slope represents. In the event that we see a graph that we've never seen before on a diploma exam, we need to be able to figure out what things mean. This is the first one that we're going to do. We've got velocity final versus velocity initial. What I want you to do first here is come up with an equation from that graph, an equation that describes that graph. Who can tell me what equation always describes a straight line graph? This is from math class. Not quite, but you're on the right track. Good. Y is equal to mx plus b. So write down that equation. My y-axis on this particular graph is VF. M represents the slope. I'm going to write the word slope in. I don't like the symbol M because I might get that mixed up with mass. X-axis on this particular graph is V1 initial. And then B stands for the y-intercept. The y-intercept in this particular example isn't going to mean anything, and you'll see why in just a moment. Sometimes it does, sometimes it doesn't. Now what we got to do is come up with an equation ourselves that describes what's going on in this situation. We have two cars colliding. We know that conservation of momentum describes that. So let's write down Pi is equal to Pf. Let's write down m1 v1i plus, what's the momentum of the second car before they collide? 0. So let's just write down m1 v1i equals m1 plus m2, that's both cars combined, times the final velocity. Initial momentum equals final momentum. Now let's rearrange this equation that we just came up with from the momentum concept to solve for the same variable as our initial equation did, the one that came from the graph. Let's solve for VF. Take the m1 plus m2 over by dividing. It becomes m1 over m1 plus m2 times v1i. Does the rearranging of that make sense so far? We got two equations here now, right? One from the graph, and we've got one from a concept or an equation. Something relevant that applies to the particular concept that we're dealing with in this problem, which is, in this case, conservation of momentum. Now what I want you to do is cross off things that appear in both. VF appears in both. VI appears in both. You can also cross off things that appear in one but not the other. In other words, plus BI. There's no plus on the other end, the other side, so we can drop that. What are we left with? Slope is equal to m1 over m1 plus m2. If we had have done this analysis with a position time graph, we would have come up with the slope is equal to the velocity. If we have done this analysis with a velocity time graph, we would have come up with slope is equal to acceleration. If we do it with a VF versus V1I graph, we come up with the slope is equal to m1 over m1 plus m2. It's a little bit more confusing than when we've got a position time or a velocity time graph, but it's the same basic analysis that we'd have to go through to determine what the slope means. Does that make sense to everybody so far? Yeah, more or less? You can always ask me questions on it. You can always go back to the podcast and come and see me. Dan? The B is the y-intercept, and effectively I crossed it off because it starts at 0. It goes through the origin. Now, in the end, that's ultimately the reason that I cross it off. But in practical terms, I crossed it off because there was nothing added to it on this side. In the second equation here, it wasn't VF is equal to something times V1I plus something. There was no plus anything. So because there was no plus anything on the right side, I dropped it on the left side. Again, ultimately, it's because there is no y-intercept. All right. So what are we going to do with this to verify the law of conservation of momentum? The first thing that I want you to do is to calculate the slope. And you're not going to calculate the slope using this crazy analysis here. You're going to calculate the slope the old-fashioned way. The slope is equal to delta y over delta x. You've got 7 or 8 graphs that you exported from this data logger. That's not the slope you want to find now. You've already got the slope of those graphs to determine what VI and VF was so that you could plot this graph. The slope that you want to find here in your analysis is the slope of the graph that you plotted. Get the value of that slope. Then I want you to calculate M1 over M1 plus M2. And you're going to do that from your data, not from your graph, from the data. Remember, you collected data for M1 and you collected data for M2. Divide M1 by M1 plus M2 and get a value for that. If those two values are the same, then the law of conservation of momentum is true. Why do we say that? Well, look at what we've done up here. We've said in our analysis of that graph that slope is equal to M1 over M1 plus M2. But in order to say that, we've assumed the law of conservation of momentum to be true. If we find that this value equals this value, then the assumption that we made must be a good assumption. If we find that this does not equal this, then the assumption that we made is presumably an incorrect assumption. Does that make sense? So essentially, by verifying that this number equals this number, the assumption that we made to get the fact that those two should be equal to each other must be true. That will lead you to the conclusion that the law of conservation of momentum is verified here, and we know that because the slope, the value of the slope, ends up being equal to M1 over M1 plus M2, meaning that because we assumed the law of conservation of momentum to get that, it must be true. We're good with that? All right, there's your analysis, and that's effectively your conclusion as well. Was the law of conservation of momentum verified here? How do you know? So answer the question based on what you just got. How do you know? Well, because those two values are equal. How do you know if they're equal enough? By that I mean, you know, in an experiment, we rarely get two numbers exactly the same, right? So let's say they're close, but not quite. How close do they need to be in order to say that they're the same? Let's do a little percent difference. You guys have probably done that in chemistry class, right? Percent difference is equal to the experimental value minus the theoretical value over the theoretical value. Remember this? Times 100. Sometimes it's written as actual value minus theoretical value. You guys have seen this before, right? Experimental minus theoretical, yeah. Tell me which one's the experimental value. Is it the first one or the second one? It's the first one. The theoretical value is the second one. So it's the slope minus M1 over M1 plus M2 over M1 plus M2 times 100. We're going to get a value for that, and we're going to say that if that value, if the percent difference is less than 10%, the law of conservation of momentum is verified. Tanner? No.
I think in Chem we did yield and then we did
Okay.
another one.
I'm not sure what you've done. I'm not sure what you've done in chem. It's probably a context. It's probably a context thing, but the percent difference is the experimental or the actual minus the theoretical over theoretical times 100. No, it would make a difference because the denominator would be different, right? So it would make a difference, yeah. All right, so you've got your conclusion. Then you need your sources of error, which of course are just, what could have been better. It could be in terms of time management, it could be in terms of materials, it could be in terms of a procedure, it could be anything. Hey, some groups this morning came up with some pretty good sources of error. Not some fluffy ones like we made calculation mistakes. Then fix them. If you make calculation mistakes, then fix them. Okay, if you get a good source of error and then a way to improve that, then write that down. What do we got to hand in for this? What do we got to hand in for this? Well, we need variables. So I want you to write down your manipulative variable, your responding variable, and your control variables. You need data. And your data is effectively that table that's on your sheet, although you are going to recopy it, and I'll explain that in just a second. You're going to need your analysis. Your analysis is primarily the graph, but also the calculation of the slope, also the calculation of M1 over M1 plus M2, and all that stuff. Basically, anything you do with data becomes analysis. You need your conclusion, and you need your sources of error along with the ways to improve that. I want you to type this. You've got a sheet in front of you and you say, like, oh, geez, can I just fill in the sheet? No, you can't. You can't just fill in the sheet. But there's some stuff on that sheet that you don't need to put in. The problem is there. You don't need to recopy that. The procedure is there. You don't need to recopy that. I want you to put in the variables in your write-up. I want you to put in the data, conclusion, sources of error, and so on. Basically, I want you to put in the stuff that's not on your sheet, that's not complete on your sheet. So it's not really any more work to retype it than it is to just fill it in on the sheet, because you don't have to recopy the stuff that's already there. Dan? That's a good question. The graphs can be done on Microsoft Excel, the one graph, because you only have to plot one, right? It can be done on Excel or it can be done by hand. I don't really care, as long as if you do it by hand, it's neat and it's on graph paper. So either way is fine as far as that goes. And in terms of your calculations, if you want to do your calculations by hand, as long as it's neat, that's okay too. It's Microsoft Word's kind of a pain that way sometimes to put equations on. No, you don't need to print off the graphs from the Explorers. There's a lot of them, and that would be a lot of paper that would be kind of a waste. So you don't need to print those off, but you should save them just in case something's wrong. Okay? In case you got crazy data or crazy analysis, and it's like, well, what's wrong with this? If you come to me with a question, I need to be able to go back to your graphs and see, oh, well, this is what's wrong. You did the slope wrong or something like that, right? So save them, but you don't need to include them in your write-up. This will be due, usually I give you 2 days to do an activity. This will be due on Monday, February 25th, which is like 10 days or something crazy like that. 25th. Monday, February 25th, 11 days from now. You can hand it in on paper on Monday, February 25th, or you can email it to me before class starts on Monday, February 25th. If you email it to me, please put the following as the subject. Don't just say, whatever. I want everybody's subject the same so that it's easy for me to sort my email that way. Okay, I want you to type physics lab, then whatever your name is. That's going to be the subject if you're emailing it. You don't have to email it. It's fine to hand it in by paper, but if you're emailing it, it's got to look like that. Now, if you're emailing it, it's also got to be all together. I don't want you to email me part of it and then say, I'll hand in the graphs by hand. Okay, if you're handing it in by hand, it's all together. If you're emailing it to me, it's all together. So, You might have to do some scanning or whatever if you're emailing it to me. Do whatever you have to do, but I've got to get it all in one package, okay? We clear on what we have to do? Okay, again, you've got the instructions as far as the procedure goes in front of you. You've got the instructions for the data logger and the motion sensor at the back of the room. I will be around here to help you, obviously, as you have questions, and you will have questions today, and that's okay. You know now what you have to hand in, so now it's a matter of getting in our groups and doing this.
Control variables